Hello, my name is Maximilian Sprengel. I'm a third-year PhD student at the Federal Institute for Materials Research and Testing in Berlin. Today I will talk about the relaxation of macroscopic residual stresses in laser powder bed fused stainless steel 316L. The laser powder bed fusion process is an additive manufacturing process where we use a laser to locally melt up metallic powder and build parts in a layer-by-layer fashion. For this study, we manufactured our specimens via laser powder bed fusion and left them on the build plate and heat treated them for 450 degrees for 4 hours. We did this for two reasons. One reason was that we wanted to relieve peak residual stresses to prevent any sort of distortion once we cut the specimens off from the build plate. The second reason was that we wanted to maintain the microstructure that is characteristic for laser powder bed fusion. Now, unfortunately, once we started cutting different shapes or extracting different geometries from the generic as-built shape, we faced distortion. So the residual stresses that were still remaining on our part were so high that the material started bending. And now we have to ask ourselves, well, although we applied a heat treatment, what are the remaining residual stresses, especially when manufacturing different shapes or cylindrical shapes from this starting block and where we don't see any distortion? What are the residual stresses remaining in this part? And also, what other post-weld heat treatments can be applied to laser powder bed fusion? So what do we know from welded austenitic steels with respect to stress relieving heat treatments that we can read across to the laser powder bed fused parts, having in mind that they have completely different microstructures? This brings me to the aims of the investigation. So we will determine the residual stresses in final specimen geometries. By final specimen geometry, I mean a specimen that was extracted from this generic as-built shape. So for instance, tensile samples. And we will focus on the residual stress range. So we'll look at the delta between the maximum and minimum residual stress in that specific geometry. Then we will focus on the residual stress distribution after the first heat treatment at 450 degrees for 4 hours in the SENB geometry, with the aim to further look into how the residual stress relaxed when you apply an additional heat treatment at 800 degrees and 900 degrees for 1 hour. Why are we interested in these temperatures? In fact, we know from post-weld heat treatment of austenitic steels that when we apply 840 degrees to 900 degrees for 1 hour per inch of thickness, we can obtain an 85% relaxation. However, we know also that welded austenitic steels, from a point of microstructure, how the residual stresses are distributed, is all very much different to the laser powder bed fused material. And we aim at understanding whether this kind of heat treatment can be applied to our laser powder bed fused material. We manufactured our specimens on a SLM Solutions 2080 HL LPBF machine using gas atomized spherical stainless steel 316L powder. You can see the composition in weight percent over here. A meander stripe scanning strategy was applied, thereby the scanning vectors were aligned with the geometry. Also, we applied a rotation by 90 degrees between each subsequent layer. In this study, we're interested in determining the triaxial residual stresses in the bulk of our specimens in a non-destructive manner. We do so by using Neutron diffraction. In fact, we use the lattice spacing as an atomic strain gauge. We can determine our lattice spacing using Bragg's law, which connects the lattice spacing to the wavelength of an incoming radiation. If we then have a suitable stress-free reference, we can calculate our strain, and then if we do so in 3 orthogonal directions, we can calculate our triaxial residual stresses using Hooke's law. Now, how does it look like during a neutron diffraction experiment? We use a set of slits and collimators to define our gauge volume. Thereby, we will determine the strain along the scattering vector, which is the bisectant between the incident beam and the diffracted beam. If we zoom in, the gauge volume used for this study was 2 by 2 by 2 millimeters. You see our gauge volume inside of the specimen with the direction of the scattering vector. And what it basically means, thinking back about the methodology of neutron diffraction, that we do have to translate and rotate our sample so that we acquire the stresses in different positions. Starting with the relaxation of residual stresses resulting from specimen preparation, we are looking at when extracting different geometries from this as-built prism, how the residual stress ranges change. So we start off with a tower geometry, which is a geometry that is subsequently used to machine tensile samples. We keep a constant cross-section, but we reduce the height. What does it mean for our residual stress ranges? Again, the stress range is the delta between the maximum tensile residual stress and maximum compressive residual stress. And we see that our stresses in the build direction remain fairly constant, whereas the other stress directions are relaxed. So despite the fact that we reduce the height by 35%, we only see a very small effect on the build direction. Now, moving to another geometry, the SENB geometry, which has a shape where we reduce the cross-section, but we almost maintain the same height. The stresses in this geometry are reduced from 800 megapascal down to a maximum of 400 megapascal. So by reducing the cross-section by 55% roughly, we have a relaxation of up to 50% in the build direction. I have to note here that these SENB specimens were heat treated before the actual manufacturing of this SENB geometry was performed, but we'll come to the effect of the heat treatment in a later stage. The other geometries we looked at were cylindrical. So from the as-built prisms, we extracted high cycle fatigue or low cycle fatigue specimens, creep specimens and tensile specimens, which had different heights, as you can see, and also the diameter changed. And what we've observed is that when determining the residual stresses in the gauge section, so we have a heavy cross-section reduction compared to the prism, we see that independently of the height, the residual stresses are heavily reduced when compared to the as-built prism. So there's a very large effect on the stresses in the build direction. This also holds true from the other directions. If we go from a, let's say, larger specimen to a cylindrical specimen. Now, how does this compare to relaxation using different heat treatments? We are now analyzing the effect of heat treatments on the residual stresses in the SENB geometry. As you can see, we determined the residual stresses along two measurement lines in the notch plane of our SENB specimens. We plotted the residual stresses in the build direction versus the distance from the notch tip. And what we've observed is that it's closer to the surface, we have tensile residual stresses that are balanced with compressive residual stresses. In the vicinity of the notch tip, we also see that there's a delta between the two measurement lines. Now, what happens when we apply 800 degrees for 1 hour? We still see that there's a profile in the residual stresses along the remaining ligaments in our specimen. And if we apply 900 degrees, this gradient is almost not visible. So there are two things to note: the reduction in the magnitudes and a flat profile when applying 900 degrees. And in fact, when we think about macroscopic residual stresses that need to balance by definition over the component scale, a flat gradient is in essence an indication for almost fully relaxed residual stresses. Now we would like to compare our relaxation results with other findings in the literature, and we can do this by using the Larson-Miller equation. So we want to plot the relaxation versus the thermal effect, which takes into account the temperature in Kelvin, the time in hours, as well as a material constant for stainless steels, which is between 20 and 22. For the plot that will follow, we use the stresses in the build direction after the first heat treatment. And what we see is that our results, so 900 degrees and 800 degrees applied for 1 hour, fit a nice trend which ends in a plateau once we reach to a thermal effect of about 24, which corresponds to a relaxation between 85 and 90%. And this actually corresponds well with what is suggested for welded austenitic steels. So basically, when applying heat treatments between 840 and 900 degrees for 1 hour, we have a stress reduction of 85%, which in this case applies to the heat treatment in 900 degrees for 1 hour that was applied to the laser powder bed fused 360L. Moreover, what we can see from this plot is that since we are almost at the plateau already, thinking back about the heat treatment at 450 degrees for 4 hours, we can assume that this first heat treatment did not affect heavily the residual stresses. Now, to summarize and conclude, we determined the residual stresses non-destructively using Neutron diffraction in the laser powder bed fused 316L specimens. We looked at the mechanical relaxation starting from the S-built prism to the final testing geometry. Thereby we observed that when we keep a constant cross-section but we reduce the height of the specimen, we have a very little effect on the residual stresses in the build direction. If we reduce the cross-section, especially if we go towards cylindrical specimens, there's a very strong relaxation of the residual stress in the build direction. In the SENB geometry, we've observed that we have tensile residual stresses closer to the surface that are balanced with compressive residual stresses in the bulk. This is the way the residual stresses distribute in laser powder bed fused specimens. And we've seen that although these SENB geometry were heavily machined and they had been heat treated for 450 degrees for 4 hours, there's still compressive stresses of up to minus 300 megapascal that are balanced with tensile residual stresses of 250 megapascal. By applying then additional heat treatments, we've seen that a stress reduction of about 85% can be obtained when using 900 degrees, which corresponds well to stress relieving suggestions for welded austenitic steels. With this, I'd like to thank you for your attention, and I'm open for questions.